Hello there and welcome back. I am Oris Schillinger and this is a tutorial on how to reconstruct 3D magnetization from a series of electron phase images. In the previous video we looked at how to align the phase images to create a geometric model of the sample and how to position all of the images correctly in 3D space to define how we want to do the reconstruction. And now let's have a look at how to get the magnetization with the best quality that we can. Like before, we import all the modules, we open up the data that we had last time and have a look at the results of our previous alignment. We made a geometric model representing our sample. Here are a few projection views of it from the sides. But for the 3D reconstruction, we want it to run as fast as possible, which means we want to get rid of as much of this empty space as we can. So in practice, we can see that the last slice in the X direction, where we actually trust our model and see our sample, is around 10. And there's also some empty space in the front. I have a function here which does all that for us. The only things we need to specify is the last slice in X that we trust, and also how much boundary charges we want. Because we know that our sample in real life extends further in the X direction, we add a layer of, well, free magnetic material which will not be regularized to compensate for what we cannot see. And this will redefine the alignment we did last time to maximize our reconstruction efficiency. I guess a note of warning. This video will include pauses when we wait for the code to compute, both 3D reconstructions and redefining the geometries. It takes a while, and I will mark which parts of the videos can be skipped. Okay then, we have now redefined the model, and as you can see there's a lot less empty space, and we have a layer of boundary material to compensate for magnetic material, which still creates magnetic fields, but is not visible within our model. And the mask we created is very similar to the raw mask that we would generate. Okay, let's save that for accessing later. And we see that within our 3D reconstruction, there will be 45,000 free variables. To definitely find the minimum and the optimal solution, we would need to run our reconstruction for that many steps, but we don't really have time for that in this video, and it does usually converge to a very good approximate solution much faster. So instead I will run the reconstruction for 1,000 iterations instead of 45,000. And the regularizer strengths are close to optimal, determined by trial and error previously. but let us see what results we get. This again is a whole bunch of numerical optimization, which will take around 2 minutes to compute. Okay, the reconstruction finished. Let's save the results just in case and inspect what we can see. Okay, the cell is finished executing. So this time around, when we used better defined regularizers, we can see that the reconstruction is a lot more believable. The magnetization values we get are more or less within the expected range, and they are a lot more uniform except for a few errors here and there. If we look at the direction of each reconstructed magnetization, this is much closer to what we found when using a double tilt series as described in the preprint that I will include in the description. And we can see the domain walls in the center much better. You can see that there's a vortex crossing the majority of the structure, and on the backside we still see the vortex here, but a bit differently than we did in the quick and dirty reconstruction we did in the previous video. And a quality evaluation for this, the first one, is the maximum spin angle. We measure the maximum angle between neighboring magnetic moments in the entire reconstruction, and we plot a projection of the maximum in each column. We can see that there are two areas which were not resolved, and magnetization behaves wildly. These are what we call null zones, or where when experimentally taking the images, the magnetic field components cancel, and we effectively have no information of what's there. To correct these, we would use a second tilt series and reconstruct both of them simultaneously, but that has not yet been automated in the code and requires too much human input. I will include a tutorial on how to reconstruct two tilt series later on, once I have that solved for a general case reconstruction. And this also shows us where the domain walls are as well, because well, the center of the vortex will have highest angles between neighboring spins. It also confirms that the majority of the sample, it is mostly uniform and has reconstructed correctly. So we can also, in terms of quality, have a look at the residuals. Here we plot the experimental, simulated, and the residual phases in each image. And we see that reconstruction does a fairly good job at replicating the experimental images. And we can have a look at this for every tilt angle and see that it is in fact functioning fairly decently. Now, further diagnostics to assess the quality of reconstruction. We can have a look at the histogram of the magnetization values. It seems to peak at a mostly single value. The material we have here is mostly uniform, but we know that the magnetization magnitude drops off towards the edges of the legs of the sample. And this is pretty much what we are seeing. It's mostly uniform material, as we would expect, but it has some variation in part due to the reconstruction, in other part due to the fabrication. Then we can also perform optimal estimation diagnostics, which allows us to calculate the point spread function and error propagation for a single voxel in the reconstruction. So we select a voxel in this part of the volume, and we run the reconstruction. In this part of the code, it tries to estimate the Hessian matrix, which we can use to propagate the errors. Computationally, this is as expensive or as complicated as doing the reconstruction itself, but we are less worried about the precision, so 200 iterations should be more than sufficient. And it also calculates this for all three components, x, y, and z, of the magnetization separately. Okay, our Hessian matrix estimation is finished. Yeah, we have results. We have measurements of the magnetization in that particular pixel in all directions, estimation of the amplitude, and of the spatial resolution. The further cells here quantify it in a more reliable way. Here we use the results to calculate an average full width of maximum of the point spread function, which in this case is 71 nanometers. It is worse than what I have published in the preprint, but that's because we only use one tilt series and therefore need to use a strong regularizer. Then we can also estimate error propagation. So here there will be some error from misalignment of the images. So if we compare that to the mean magnetization value to get a percentage error. But yes, if we were to force the reconstruction to match one of the images perfectly, we would expect this is 11 millitesla error on that particular pixel, which would translate to about a 1.8% error. Also, we can evaluate the effects of measurement noise. In the simplest case, we use that by looking at phase reference images. If we measure the phase twice in a vacuum, we would expect both measurements to have the same values. But in practice, if we take their difference, they are not identical. And the standard deviation of the noise we can measure, and if we input it into our code, we see that the phase measurement error would introduce about a 0.7% error on the magnitude of each magnetization measurement. Combining these, we see that we have a total precision of 1.9% for measuring this particular voxel. And the last little bit of quality assessment is the Fourier shell correlation. It is not entirely applicable to this method because noise is automatically suppressed by the regularizers in the reconstruction. But it is still a good estimate of how much noise we have left. And if we have a look at this, we see that our reconstruction correlates with itself really well, even up to very close to the Nyquist frequency, or in case of the Z component of the magnetization, which is much smaller in this sample than magnetization in the other directions. Even the highest values are almost entirely determined by the regularizer, which, being a theoretically defined function, correlates really well. But nonetheless, we have performed a 3D reconstruction from a single tilt series. We found spatial resolution, which is effectively the point spread function of the reconstruction. And we have also evaluated the precision on the measurement of a single voxel based on the errors that the uncertainty in the phase measurement and the misalignments of the images we introduce. And if we want to do better, we would need to use two tilt series, but aligning two tilt series with each other has not yet been automated, and I will include a tutorial on that as soon as I have come up with a generalized solution that should work for most samples. Thank you very much for watching, and I'll see you in the next one.